Welcome to Study Loop.
Okay, we're looking at question 28.68, where we have this weirdly bent wire that's essentially, it's a third of a semicircle that's bent around, and we have two different, there's an inner radius here, which I've labeled R1, that's 20 centimeters, which I've converted to meters, 0.2 meters. And then the outer radius, R2, is 30 centimeters, and I've converted that to 0.3 meters. And this angle here is 120 degrees. So again, that's, since one whole circle is 360 degrees, this is 1/3 of a circle. And the current here is going along this direction. You can follow it, and the magnitude is 12 amps. And we want to figure out what the magnitude and direction of the magnetic field is due to this current loop at point P right here. So to do that, we need to use the Biot-Savart law, which I've written up right here. And one key thing to notice first is that we have this cross product, the dl, which is in the direction of the current, cross r, which is the vector that points from the point to the section of wire that we're considering. So if we look at these two little, this vertical point and then this little end cap over here, when we think about the direction of the current, that's going to be pointing straight down. And then r is also going to be pointing straight down. So these two vectors are parallel, which means there will be no contribution from the magnetic field from these endpoints, because the same thing is going to apply for this little point over here. So the contribution from these two little cap points is going to be 0. So we just need to think about the inner part and the outer part. So let's just split those up into two parts, and we can just add them together. So since there's going to be a factor of mu naught over 4 pi in both of those, I'm going to pull that out and just leave it out here for now. So we have this factor of mu naught over 4 pi. Now let's think about this inner circle with this radius. We're going to use R1 as our radius here. We have dl cross r. Now this is, the dl at every point is going to be tangent to this inner semicircle. And r is going to be the radius, so it's going to be pointing straight to the point of wire here. So those two vectors are going to be perpendicular. So dl cross r is really just going to be, actually this, I should notice that this is, over here, these are actually just unit vectors. So this is indicating just the direction of r. This isn't really indicating any sort of magnitude. This is just going to tell us the direction of r here. And since the direction of r is perpendicular to dl, this dl cross r is just going to turn into regular dl, because dl cross r hat will just be dl times r hat times sine of theta. The magnitude of r hat is just 1, and sine of theta, when both vectors are perpendicular, will be equal to 1, because if theta is 90, sine of theta is 1. So we're going to have this contribution from the first part, this inner wire, and then we're going to have the same thing from the second wire, except now this I, the current is now going in the other direction. So I'm going to turn this to a minus sign, because the current is now going in a different direction. So now at this point, we're going to need to integrate this equation. So let's think about what here is a constant and what is what needs to be integrated over. So mu naught and 4 pi, these are constants. I is just the magnitude of the current, so that's also a constant. R1 and R2 are also just constants. We know those aren't changing. So the only thing that we have to integrate over here in each of these cases is this dl. So I'm going to just pull that out so it's clear that that's what we're integrating over. I'll write this in 1 second. So we want to be integrating over this dl because everything else is a constant. So let's think about when we integrate over this dl, the integral here is really just going to be the length of each piece of wire. So the length of this inner piece of wire here, like I said, this is just 1/3 of this entire circle. So the circumference of the entire circle would be 2 pi times r1 when we're thinking about this inner circle. I'm just going to write this a little bit separately here. So the total circumference would be 2 times pi times r1, and then the circumference of the outer circle would be the same thing times r2. But we have only a third of this, so the total circumference is really just going to be this divided by 3. So this is going to be the value of our dl here, and it's going to be the same just with r2 substituted in for r3 down here. So for r1 down here. So I'm just going to plug this in because these are all going to be up in the numerator up here. And then this 3 is going to be down in the denominator right here. So hopefully this isn't too confusing. But this is the value, this 2 pi r1 divided by 3, that's the value of this integral here. And it's going to be the exact same thing over here, except we have r2 instead of r1, because the integral of this is going to be 2 pi times r2 divided by 3, because it's only a third of this big circle. So now all we have to do is plug all of this in. So when we do this, we're going to get, let's see, well, first, before we actually start plugging things in, let's see if we can simplify anything. So we have a factor of pi here. This is in the numerator. This is in the denominator. So let's cancel out those factors of pi to make it easy. Let's get rid of these. We have a factor of r2 up here and a factor of r1 down here. So let's also get rid of that. There's a factor of r2 and then 2 factors down here, so we can cancel one of those factors out. So this is about as far as we really need to go. So let's, at this point, we can just plug this in and solve. Oh, sorry, this is already integrated. So we don't have to worry about this extra dB anymore. So now this is the full integrated version. And when we plug this in and solve, we should get b equals 4.19 times 10 to the minus 6, and this will be in Tesla. So this is the magnitude of the magnetic field. Thinking about the direction, if we use the right-hand rule, we want to point our thumb in the direction of the current like this. And if we do that, then our fingers are going to be curling into the page at this point here. And similarly, if we do the same thing with the outer ring, we're going to get a magnetic field pointing out of the page. But remember, we don't, since this inner wire is closer, that's why we have this subtraction sign here, the value of the magnetic field from this contribution is going to be greater than the magnetic field from this contribution. So this one is going to win out here. So since this gives us a field that's into the page, this one is going to, the net magnetic field will be into the page.